So now that we've learned how to do basic implicit differentiation, we're going to take a special look at how to utilize this same technique when finding the second derivative. Sometimes it's not really that different, and sometimes it kind of is. So we're going to go through two different examples in this video. For the first example, we're going to use the equation y squared plus 2y equals 2x plus 1. So let's take the first derivative. And remembering this is y is our function since we're finding the derivative of y with respect to x. So that's going to do the chain rule right here. So 2y times dy over dx plus, that's just going to be 2 times, again, the derivative of y with respect to x equals, the derivative of 2x is simply 2, and 1 would have a derivative of 0. So now we can do the part where we take the dy over dx and factor it out front. So that's going to give us 2y plus 2 in parentheses, and we simply divide by that fraction, or sorry, that parentheses to get a fraction. So we're going to get dy over dx equals 2 over 2y plus 2, which we can of course simplify. Everything's divisible by 2. So for my final answer, I'll say dy dx equals 1 over 1y plus 1. Okay, so from the last video, we should feel pretty comfortable getting that far. And you want to make sure to do the step we just did where we just simplify anything possible so that when you take the second derivative, it's really not as bad as it would be otherwise. So always simplify as much as possible. Now when we take the second derivative, we're not going to have to do this step of like getting our second derivative factored and isolated because we've already isolated the first derivative. So that's not the hard step here. And remember our notation for the second derivative with respect to x. Okay, so taking the derivative of the first derivative gives us the second derivative equals, and we're going to have to do the quotient rule here. So low d high minus high d low. So again, we're taking the derivative of the y, which would be dy dx, plus 1, which would just be 0, over low low. Okay, so again, the hard part isn't isolating what we're solving for with the second derivative, it's just cleaning it all up. So we can simplify what we have so far. So that's just going to go, all of that cancels out and goes to 0. So we're left with simply negative dy dx over y plus 1 squared, but we want to solve for all derivatives in terms of y and x only. It's not very useful to have a derivative where another derivative is part of that. It's a lot of extra work. So we can go ahead and actually substitute in what we know this is equal to, which we solved for previously and got 1 over y plus 1. So we're going to actually plug that in the next step. So our numerator is 1 over y plus 1. All over y plus 1 squared. So this is a complex fraction. So now what I'm going to do is simply keep the numerator and multiply by the reciprocal of the denominator, just so I don't have a fraction in a fraction. Okay, so I'm going to have 1 over y plus 1 times, pull out that denominator. Okay, and now we can conveniently simplify this. Okay, and that's just going to be 1 over y plus 1 cubed. And there's not really anything else we can do to simplify that. That's about as nice as it's going to get. And that's all we have for the first example. Alright, so for our second example, we're going to use y squared equals x squared plus 2x. Okay, so let's take the first derivative of y with respect to x. So we're going to take the derivative here using the chain rule. We're going to get 2y times dy dx. And just as a side note, sometimes instead of dy dx, you'll see people write y prime, which you're totally welcome to do. I don't really use it that much because it is very easy to either forget or overlook a prime symbol. Whereas when I write dy dx, it's a lot easier to not forget that that's the derivative. So, just side note. Okay, that's going to be equal to 2x plus 2. This one's not so bad. So we're just going to divide on both sides by 2y. And we get dy over dx is equal to 2x plus 2 over 2y. Again, coincidentally, these are also all divisible by 2. So I'm going to go ahead and clean up anything I can before I take the second derivative. So I get x plus 1 over y for the first derivative. Alright, second derivative. So the derivative of the first derivative gives us the second derivative. And then we're going to do the quotient rule again. So low d high, that's just going to be 1, and then the 1 plus 1 goes to 0, minus high d low. Okay, all over low low. Okay, let's simplify what we can before we plug in what the derivative of y with respect to x is. I guess we can go ahead and do that here, because there's not much else to clean up. So I'm going to go ahead and make that substitution of what I know dy over dx is equal to. We're going to get another lovely complex fraction out of this. Okay, so to get rid of this fraction, I'm actually going to multiply by that denominator of y on the top and the bottom. And the one thing I just want to caution everyone about here, or I guess a common misunderstanding, is when I multiply the top by y, right? So when you look at the top, we actually only have two terms. So those two terms are what the y get distributed to. And when the y gets distributed to this second term, it really is just getting rid of this particular denominator. So it doesn't also get multiplied to x plus 1 separately. This is all one piece. Okay. So on the top, we're going to get y times y, which is just going to be y squared. Again, that second piece, it's really going to get multiplied by that whole thing, but in reality, it's just going to cancel out that denominator there. And that'll leave us with minus x plus 1 times x plus 1. And then we multiply the denominator by y. Oh, that was supposed to be purple. There. Okay, and that's just going to give us y cubed. Okay. Let's try to distribute some stuff, and something magical is about to happen. So x plus 1 times itself is going to be x squared plus 2x plus 1 all over y cubed. And I'm going to pause here. And this doesn't look like it's going to get much prettier, but like I said, something magical is about to happen. So if we go back, not to the first derivative, but to the very beginning of our problem, we're going to be able to use this relationship, this original equation setup in some of these second derivative problems to make our answers look nicer. So there's two ways you can go here. Where you see y squared, you can plug in x squared plus 2x, or where you see x squared plus 2x, we can also substitute y squared. I'm actually going to do that second one in this particular problem just so we have less pieces. So again, I'm going to take the fact that y squared equals this. Okay, I'm going to come down here, and I see x squared plus 2x right here, so I'm going to be sneaky and make that substitution. So y squared minus that piece is now equal to y squared, according to the original information I was given for the problem. And you can see why this is going to make our answer look a lot nicer. Because really, I'm going to have y squared minus 1 all over y cubed, and those magically disappear for me and leave me with a second derivative of -1 over y cubed. Wonderful. Now some of us are like, there is no way I would have ever known to plug that in there. But just as a fun fact, remember you also could have plugged in or substituted in for y squared, x squared plus 2x, and had that minus x squared plus 2x plus 1 all over y cubed. And then that would have ended up canceling out with that, still giving you a -1 over y cubed. It's okay, I'll be done in a second. Sorry, my dog is really excited again about implicit differentiation. Alright, but that basically concludes this example. Trust me, we're going to practice this type where the original problem shows up in a way to help us simplify things. But just take comfort that, and if you don't necessarily see where to substitute those things, it's not going to make or break you. It just takes some practice. This concludes our video on implicit differentiation with second derivatives.